Thank you, everyone, for being here. I'll be talking today about generative health, which is a mix of two other sessions going on right now, generative AI, healthcare, and also in computer vision. A friend of mine who is a clinician at ER, he once asked me, do you know what's the largest or the biggest predictor of mortality in the ER? And I thought, it's probably the age of the person, or maybe the gender, or maybe, where is this person coming from? And he actually told me, it's the thickness of their chart. It's how many times have they come back to the ER? Is what is written there? Once a person gets sick and is serious, they keep getting sick over and over again and getting admitted over and over again to the ER. And that made me think in terms of, as a data scientist, that's something that the model would probably pick up on and say, hey, this is a predictor of mortality if you're trying to predict something about what's happening. But that's totally a bias. It's not a causation, right? It's not because you have a thick chart that is actually causing you to die. It's just a correlation there. And it's a type of biases that we, developing models in healthcare, have to deal with and try to find ways to fix all the time. My name is Pablo Damasceno. I'm a principal data scientist at Janssen Pharmaceutical. My background, I am a physicist by training, using computer simulations to develop materials back in the day. About 5 years ago, I fell in love with the field of machine learning AI, and I switched to the field of medicine. In particular, here on the right is a model that we developed and deployed at UCSF that uses AI to measure the tumor volume in a brain tumor over time. And if a patient comes to the hospital and has their brain scanned, instead of the doctor eyeballing and trying to find out, did this tumor grow over time, our deployed model calculates this volume, shows a plot to the doctor and say, hey, it has grown by this many centimeters. And then they can use this information to make a decision on whether to do surgery or not. At Janssen Pharmaceuticals, part of my job is I lead a team that works with videos, one of which is endoscopy videos. I'm saving you guys from looking at some of those videos here today. But one of the issues that we have when we're trying to develop ML models to understand the video and help clinicians find out what is the disease severity along this video, part of the issue that we have is that we have a lot of biases. Sometimes it's the population, is the fact that when you have a clinical trial, you might have recruited more males than females. You might have recruited someone with older age or younger age, and all of these are biases that when you're training an algorithm, you're making the algorithm perhaps make better decisions in one set of population than another. Another set of biases that we have to deal with all the time is what was the hardware used in a clinical trial, what was the software used. Again, all of these are biasing our algorithm to perhaps perform better in one hardware or software. And one that's incredibly tricky is when the data inherently, the data itself, is biased. And in particular, if the data is imaging, and if that image contains something that's biased, it just makes it very tricky for us to work with that. And that's where the excitement comes with generative AI. In particular, this is from another work that we have done some years back, trying to predict mortality of patients with COVID-19. And one of the things that the model was picking on all the time was, does this patient have a pacemaker? Or is this patient on a ventilator? And again, there is a correlation, obvious correlation there, but it's not a causation. If you go to a ventilator for an hour, you shouldn't see a crazy increase in the probability of your mortality as soon as you get out of these ventilators. So if you take a chest X-ray with, for instance, a ventilator or a pacemaker, ideally, you would like to remove this information out of the image so that this is not a source of bias anymore when you're training your model. Removing might be tricky because when you're removing something from the image, and this is what I've done here, the original image was generated by AI. The second image was also generated by AI. But when you're removing something, you have the risk of also removing some important information, right? Maybe this is a lung, maybe you could see COVID there, and now you remove part of the image, now you cannot see anymore. So what we're doing instead is adding a lot of this information that is a source of bias. For instance, in this case, a pacemaker. Can I add this to the image in a way that now I'm balancing my data sets, and doesn't matter if you're healthy or if you have COVID, I have the same number of people with and without the pacemaker, and now this is not a source of bias anymore. Now, just a quick rundown. If you're not familiar with diffusion models, what are they? How do you train them? The idea of diffusion model is actually really simple, but the advances in very powerful GPUs nowadays is what made it completely like revolutionize the field. This is a 2020 paper, really recent, and the idea is you take an image, and then you add some noise to it, and then you say to the model, can you remove the noise and bring back the image that I have? And then you do that over and over again. Now you add a little bit more noise, 20% of noise. Can you go back? You add 30% noise. And you keep doing that with thousands of images, hundreds of thousands of times, this process of adding noise, removing noise, adding noise, removing noise. And if you do that for enough times, you just give some noise to the image. And if the model has seen enough faces, it starts to just generate a bunch of different faces. And what's incredible about this is that you see that the images that are generated, you can do this training with 1,000 images, and you can generate 1,000,000 faces, and you can see that they're all different. It's a little bit of a mixture of different people. You're going to see, oh, it looks like you got the nose from that person, the hair of this other person, the color skin of this other person, and created someone completely new. Does it work for medical imaging? If you go today to DALI or Midjourney or any of those places, and you try to say, give me an X-ray. You don't even have to say a chest X-ray. Give me any X-ray, and you might get something like this. I've tried with every single possible sentence that you can come up with for chest X-rays, hand X-rays, MRIs. It just doesn't work for medical imaging because, thankfully so, it was not really trained on medical imaging. It was trained on images you find in the real world and not medical data. So then we needed to train the model first. So what you do is exactly what I described. You start with some hundreds, maybe thousands of chest X-rays. You add some noise to the image, and you give to the algorithm and say, hey, can you remove the noise out of this image? And you do that again and again and again and again. And if the model has only seen chest X-rays, tens of thousands of them, they're different, male, female, old, young, you can give some noise and say, pretend you're doing the training, get something out of this noise, and it just generates a chest X-ray. And what you see is that when you do this training, so does this work? This is how you train. On the top here, I have different snapshots during the training process. So first 10 or so steps, I started from one of those pre-trained models that already could make a face, it could make a car, already had some knowledge of the normal scenes that you would see in the world. And when I asked you to generate a chest X-ray, started by making some weird images, but as you go on the top, the images start to get better and better, up to the point that after training for a day, I took a bunch of those images, sent to, again, my a clinician friend who works in the ER, and he called me immediately. He's like, where did you find those X-rays? Those are weird. And I said, what do you mean those are weird? And he said, a bunch of them are normal. There is one person that the heart is flipped. The heart is completely flipped in the wrong direction. And there is another person, I think it's the second one here, doesn't have a heart. He's like, what is going on? Like, and I had to tell him, like, oh, those are AI generated. He's like, oh, thank God. I was gonna run to you and said, my friend, whoever sent you those is in real trouble. How are they alive? But what was super interesting to me was that in the same way that, as I mentioned, when you're asking to generate faces, it generates one nose of a person with a ear of another, with a face of another. To flip the heart entirely, it really takes some skill, right? It's not like it really means that the model started to create a heart independent of another part of the model that started to make the torso, and then they had to match at some point. But it has an information of what a heart looks like because it made the entire heart. So that was very fascinating to me. And on the right here, you have the image that I've been using with a pacemaker, which just by looking at those images, I imagine this is how a pacemaker should look like, but it's really detailed. I was impressed. So this is something we're actively working on, this area of can generative AI be used to remove biases, in particular artifact biases. And the suggestion here is that you might be able to. And also you might be able to use this to generate or to remove biases in the population as well. So if you had only a handful of scanners or scans from maybe a population from Brazil, and you want to enhance your data set and increase the number of images from this population, you might be able to feed those and say, okay, this is 100 images from this population from Brazil, make me more that look like this. Or another thing that happens all the time is if you have a lot of images from one scanner, GE, and then you have a few from Siemens, and then your model doesn't know what to do with the Siemens scanners because it has not seen enough. Use generative AI to just generate hundreds of other images that would look like if they came from the Siemens scanner. So this is quite promising, and in the next, I believe, 8 minutes or so that I have left, I'll talk about the second part that's really exciting to us, which is a combination of those diffusion models with the large language models. And this is also something that came up really recently, so from basically last year, where what was done was to combine the power of large language models with the power of the diffusion models, so that now you could do something like create a chest X-ray showing a pacemaker. And because the large language model understands what you mean by X-ray, what you mean by pacemaker, it would generate this image in the shape that I was showing before. And just to make explicit what the difference is, before I was just training on tens of thousands of chest X-rays. What this allows us to do is to train on hundreds of thousands of any X-ray, foot and hand and any part, and say, I want you to generate a hand X-ray, a left hand X-ray with a broken bone. And that would really enhance the data set that you can use to then train your models. Again, does this work? The way I was looking into testing if this would work was with a simple task that also we deal with all the time. Sometimes we have to segment a bone, and it takes someone a long time to go around a bone and draw where the bone is. And if they have to do that for hundreds of bones in a hand or feet, it just takes them many, many hours, and they do like 2 hands, 2 feet, and they're tired. Can we use the power of diffusion models and the power of large language models to say, here's an example of a hand without any segmentation. Here's an example of a hand with 1 bone segmented. Can you segment 2 bones, 3 bones, 4 bones, 5 bones, and save all this time of the doctors having to do that? One issue that I did when I was making this experiment was I only segmented the middle finger when I was generating data to the model. And then I asked the model, can you generate an X-ray of a hand with 2 fingers segmented? And that's what it did. Because I only segmented the middle finger, it basically essentially generated 2 middle fingers in 1 hand. And it did what I asked it to do, in a sense, which was to generate an X-ray of a hand with 2 fingers segmented, but not quite what I wanted, right? This one I didn't even have to send to my clinician to know that this was not a very good chest or hand X-ray. So those models do hallucinate in the same way that large language models have those hallucinations of just generating content. And essentially, it's part of the issue if you don't train the models long enough, but another part is what I was mentioning, that when you're generating images, the image is being generated from different parts at the same time, kind of like in parallel. So it's making one finger, and the model doesn't know that there is another finger being generated on the side. So another thing that I tried was, okay, you seem to be clever. I'm going to try to be even more clever. I'm going to take one image. I'm going to segment all the bones of this one image. And I'm going to write a script to take all the possible permutations of segmented and not segmented, because then with one hand and all those different bones that I segmented, I can generate a boatload of training data. And I'm going to say, here's one hand with the pinky segmented on the second bone, and do all those permutations, and now I have a boatload of data. You're not going to fool me with this whole thing of just segmenting the middle finger. And also a bunch of images without segmentation, train the model again, and when I run inference, I'm trying to say, okay, can you segment the proximal phalange of the middle finger? You did it right. Proximal and the middle phalange on the middle finger, you did it right. Proximal and middle and distal phalange of the middle finger, and essentially all the different fingers, it did it all right. Like, okay, this seems to be working. Until I noticed all the images were the same. Because I was training essentially, again, in just one image, and I was doing this trick of doing all those different permutations, it doesn't matter where I start from, and it doesn't even matter if I start from a hand X-ray and I say, hey, segment the phalange in the middle finger, you would morph the X-ray that I had into one of the examples that it had seen before with a segmentation and saying, is that what you want? So they're also prone to image memorization. If you don't have a large enough data set, you just will not be able to generate data. So there's no magic there, right? If all you have is 10,000 chest X-rays of adults, you have one chest X-ray of a child, and you say generate 200,000 more like the child, it's just not going to work. It's in one, it's going to give you that one back. And this is really scary, because one of the promises of Gen AI, and there are many, many companies out there saying we can sell you data, is that they say, oh, the data is going to be, there is no more problem of identification. You're not a patient anymore because this data has been generated by a computer, even though if you sold your data or if some hospital sold your data and we purchased, now all of our data is generated. That's not quite true. There is some memorization that's possible. Maybe if in the chest X-ray there was your name on the corner of the chest X-ray, what this model can do is then propagate this name again and again and again and again, and all of a sudden you have this biased data set that is basically you were multiplying this bias. So this is what I have today. I think this is it's a field that is very new, it's very exciting. We jumped on this to really try to understand what are the boundaries of using those diffusion models for medical imaging. Some things that I've noticed was that those models are prone to hallucination. You can see hands, and in particular, if you use Midjourney or any of those diffusion models, you see that generating hands is an issue. You see like beautiful people being generated, and then you look at their hands, they have 5, 6, 7, 8 different fingers. They also are prone to memorization of the inputs. If you don't have enough images, you might be prone to just getting those images back from the training set. But we're really excited with the potential to reduce the bias just by, if you have a large enough data set and you know where your biases are, to just use those models to generate more of the images that you're excited about. So. I think I might have 1 minute for questions. And yeah, one more thing that diffusion models cannot do is that they cannot write anything. So if you, this was my best attempt to get it to write questions.